Hello! Alright, today I'm going to be doing a paper with you. This is mechanics. So we're looking at mechanics. It's November 2023, and this is paper 4.3. So let's just dive right into it. Okay, our first question is a particle is projected vertically upwards from the horizontal ground with a speed of u. Okay, so we're looking at projectile motion, and these are going to be our Suvat equations. So our initial speed is u meters per second. The particle has a height of s above the ground at 3 seconds and 4 seconds after the projection. Okay, so if it's at a height of s at 3 seconds and 4 seconds, that means as it's going up, it's going to be a time of 3 seconds, and as it's coming down, it's going to be at a time of 4 seconds. Okay, find the value of u and the value of s. Okay, this is an interesting question. What else we know for particles that are projected is our acceleration is always gravity, and in this case, we're just going to take it as -10. We don't know our displacement, but we've been given a value of s at a specific height. And then we've got our 2 times, 3 seconds and 4 seconds. So what I'm thinking here is if I've got s is equal to ut plus a half at squared, if I plug in t is equal to 3 and t is equal to 4, it should have the same displacement at that point. Okay, so if I plug in 3 seconds plus a half minus 10 and 3 squared, that's 3u minus 5 times 9 is minus 45. Okay, so I've got a formula for that, and then I've got another one. So this is going to be 4u, that's 4 squared. I'm going to tell you why this works just in a minute. So 4 squared, that's minus 80. Okay, and so if I equate these to each other because they're going to have the same height at that point, and I do think these are solvable in more than one way, definitely. This is just the way that I thought of best. Okay, so 35, so it's got an initial launch speed of 35 meters per second, and what do they want to know? Find the value of s and u. Okay. So I'm just plugging that back into one of my other equations. S is equal to 60 meters. Okay. Let me tell you why. I should have explained why before I started, but anyway, what you need to know is that these equations, these are vector equations. So this is an equation for displacement, not distance. Okay. So if I plug in all my initial values, so I'm going to say up is positive, but this thing is automatically in a quadratic shape. It goes up and then it comes down again, because now in this case I've got my negative acceleration. So if I have my quadratic, it's going up and down. So when I plug in my 3, well, it's going to have the same displacement at 2 points, at the point 3 and again at the point 4. So I think it might be a little bit confusing. Some people might think that you have to take up, for example, as positive, and then when it's coming down, you're going to change your acceleration to negative. But just practice these questions when you are working in one equation, like my blue arrow here. What's happening is that this particle, if I take up is positive initially, then my gravity is going to be acting down, acceleration is acting down. But if I keep going along the direction of motion, even when the particle's on its way down, gravity is negative because it's now accelerating in the opposite direction. So as it was going up, it was decelerating. Now it's accelerating, but it's in the opposite direction. So it still stays a negative sign. Okay, so this is kind of a trick. I do think there's more than one way to do it, so maybe explore the question a few times in a few different ways, but that is what I could see was the easiest as I started, is to go with one arrow and to know it's going to have the same displacement at these two different times. Okay, let's jump into our next question. This looks interesting. Okay, so here we see a machine for driving a nail into a block causes a hammerhead to drop vertically onto the top of a nail. Okay, so the mass of the hammerhead is 1.2 kgs and the mass of the nail is 0.004 kgs. The hammerhead hits the nail with the speed of that and it remains in contact. Okay, so what I'm busy picking up here is this is a momentum equation. These two things are colliding and now they've kind of coalesced because they're going together. It remains in contact with the nail after impact. The combined hammerhead and nail move immediately after the impact with a speed of 40 meters per second. Okay, calculate V, giving your answer as an exact fraction. Okay, the hammerhead hits the nail with a speed of V. Okay, so the nail is going to be going, so I've got M1, U1. This is my equation of conservation of momentum. M1 V1 plus M2 V2. Okay, so I've got my hammerhead is going down. In this case, I'm going to take down as positive. So whenever you're doing the momentum question, you must pick a direction that is positive. Okay, we don't know with what speed it hits it, but it hits it at V. Then my nail, I'm going to just say it's got no momentum initially. And then here, I should have actually combined these. 1.204 is going to be my total mass if I add those two together. And that is with a velocity of 40 meters per second. Okay, so what I did there, instead of writing down this equation, let me just use that. You've got your M1 plus your M2, and they are going at a coalesced speed. Okay, so if I were to work this out, 1.204 times 40, and then I'm just dividing it by 1.2. Okay, so an exact fraction, my velocity is 602 divided by 15 meters per second. Okay, so although that looks like a strange number, we just need to do what they said in terms of the instructions. So hitting it, well, giving our answer as an exact fraction. Okay, the nail is driven 4 centimeters into the wood. Find the constant force resisting the motion. Okay, so now we're going to find the constant force resisting the motion. So let's just assume the particle. This is my hammer and my nail. They are going down. So they've got their weights is what is helping them go down. So 1.204 times gravity is what's helping them go down. And we've got a frictional force acting against them going up. Okay, so we can work out our acceleration. That would be the first thing. I don't think there's any other forces. We've got the weight of them. There's no longer a driving force because it was dropped onto, the hammerhead was dropped onto the nail. Okay, so we've got minus friction plus 12.04 is equal to 1.204 times A. So the acceleration of these particles, oh, we can't work this out yet, but we know it's gone 4 centimeters. Okay, so I'm going to come back to that because I don't have acceleration and I don't have frictional force. So there's two things I don't know. Okay, so now we know it's starting with a speed of 40 meters per second. We're going to want to work out the acceleration because then we can plug it into this formula. Our final velocity is 0 because it comes to, it becomes stationary after 4 centimeters. Okay, and then 4 centimeters divided by 100 is 0.04 meters. Okay, so let's use Suvat here. V squared is U squared plus 2AS. Okay, so it comes to rest. It's starting at 40. We expect this to be deceleration. We expect our answer to be negative. Okay. All right, this is quite a huge number. So it's negative 20,000 meters per second squared. Okay, so we did expect it to be quite a big number. All right, let's go back up to the top here. So I haven't necessarily written this in the most convenient way, but anyway, let's keep going. 12.04 is equal to 1.204, and this is negative 20,000. So the deceleration, we need to make sure that we put that in there. Okay, minus 12.04, and then the whole thing is actually positive, so that's 24,092, and I get 0.4 newtons. Okay, so if we were to round this off to 3 significant figures, 24,100 newton. That would be my final answer in terms of significant figures, but so long as you have more significant figures than less, it would probably be acceptable. Okay. Next question. A block of mass, 8 kg, slides down a rough plane, inclined. Okay, so we're going to have friction, and because we've got an incline, we need to include our weight component going down. Okay, draw diagram. Okay, I haven't even read the rest of the question, but anyway, so there's 8 kgs. So that's 80 newtons. It's at 30 degrees. So we know that's 30 over there. And let me just draw this a bit differently. That's 30 over there. Okay, it's on a rough plane starting from rest. The coefficient of friction between the plane and the block is mu. The block accelerates uniformly down the plane. So that means our friction is acting up. Okay. Draw a diagram showing the forces acting on the block. Okay, so my weight component will actually be split into my x and y, but for now, I think I'm just going to leave it like this. So you've got your weight. You've got friction acting up because the block is moving down. So I would leave my drawing something like this. Okay. Find the value of mu. Right. So what we need to, it looks like we're going to also be using a little bit of Suvat and Newton's second law in this block. So we know our frictional force is mu times R. In this case, our R is just going to be acting opposite our weight component. There's no other forces in the y direction. So I know some of my forces in the y direction is 0. So I'm going to say R minus 80 cos 30 is equal to 0. So my R is 80 cos 30. So now we need to work out our frictional force, because we're aiming, at the end of the day, we want to get to mu. Okay, so we first have to figure out via a different route what is R, and we've just got that. Now we need to work out what is our frictional force. So I'm going to use Newton's second law here. The block accelerates uniformly down the plane. So sum of my forces is mass times acceleration. If I look at the block, I'm going to look in the line of motion. So it's going down the plane. So the only forces acting on the block in that line is my friction that's holding it back. And I'm taking down to be positive. And then I've got my 80 sine 30. So that's the weight component that is pulling it down. That is equal to my mass, 8 kgs, times my acceleration of 2.4. So this helps me to figure out my frictional force. 8 times 2.4 minus 80 times sine 30. Calculate is in degrees, watch out for that. And then I'm going to divide by -1 to get my frictional force, which is 20.8 newtons. And now I can go directly. My frictional force is mu times r. So I've got my 20.8, my mu, and then I've got my 80 equals 30. So I'm just keeping it like that so that I can keep all my decimals. Okay, but you could have worked it out earlier. That's not a problem. I'm just going to give this to you now as a fraction. So 13 root 3 over 75. But that could also be, if I round it off, I'm getting 0.300. So I would put the 00 there just to show that I have accounted for 3 significant figures. Okay. All right, find the speed of the block after it has moved 3 meters down the plane. Okay, so now we're just going to jump into Suvat. Its acceleration is 2.4 meters per second. It starts from rest. We want to know the velocity when it reaches the end, well, when it's reached 3 meters. So that is just a straightforward Suvat question. Okay, I wonder if you know your Subats off by heart. You don't need to, because they are in your MF 19. But it does help to be very familiar with them. Okay, 2 times 2.4 times 3. And then I'm square rooting everything, and I am getting an answer here of 6 root 10 over 5. And that is also 3.79 meters per second. Let's just see what did they ask for. Find the speed of the block after it's moved 3 meters down the plane. Okay, so it's perfectly fine to just have the 3 significant figures. Just make sure that you do give, don't round off too early. Okay, cool. And that looks good. Next question. A car has a mass of 1,600 kgs. The car is moving along a straight road at a constant speed. So every keyword counts. Constant speed. It is subject to constant resistance of 480. So you could maybe just draw your car. I normally draw it in my lines, but I'm going to avoid doing that right now. So it's a horizontal road and it's a constant speed. Okay, and there's a constant resistance of 480 newtons. Find in kilowatt the rate at which the engine of the car is working. Okay, so kilowatt, we're talking about power. We've got 2 formulas for power. The one is work done divided by time, or our driving force times our velocity. Okay, so in this case, I think the easiest is going to be our driving force times our velocity. Okay, what we need to know about a constant speed, if it's going at a constant speed, it means the forces in the line of motion are equal. They cancel each other out. So we've only got friction acting against it. So it means our driving force is also 480. Okay. So I'm just going to put that somewhere down in my lines. And then I'm going to say power is my driving force times my velocity, which is 480 newtons. And it's going at 24 meters per second. And that gives me power, and they want power in kilowatts. So I'm just going to round off. It's 52 kilowatts. Okay, 11.52 kilowatt. So it's 115,000, 11,520. Okay, goodness. All right, the car now moves down a hill. Okay, as soon as it's moving down a hill, we need to account for its weight. It now moves down a hill. So I'm going to say it's going in this direction. It's angled at theta. Sine theta is 0.09, so they've given us the angle. The engine of the car is working at 12 kilowatts. So I just put it into watts immediately because otherwise I sometimes forget to. The speed of the car is 24 meters per second at the top of the hill. So here it's 24. 10 seconds later, so time is 10 seconds. Our distance it's traveled is 280 meters. And the speed at the bottom is 32 meters per second. Okay, so it's definitely accelerating. Okay, given that the resistance is not constant, okay, so we can't go into Subat here. But anyway, it says use the energy method to find the total work done against the resistive forces during the first 10 seconds. Okay, right. So I love these energy equations if you understand what's going on. So whenever we look at energy, I look at 4 different types: potential, kinetic, work done by driving force, and work done against friction. Then what you need to do is you need to take a snapshot of before and after. Okay, so at the top of this hill, the car has potential energy. So I'm going to put everything it has, or anything that's given to the system, goes on the left. It has potential energy, and the engine is doing some work. Okay? It does, oh, and it has kinetic energy. So you must just check, always go down your list. It's got some kinetic energy because it's already moving at the top of the hill. Okay. Then, this is all initial, and that must be equal to all the energy afterwards. At the end, it doesn't have potential energy relative to the ground, horizontal ground, let's say, or even, it doesn't even matter if it's a horizontal ground, but just relative to at the bottom of the hill, it's got no potential energy. It does still have kinetic energy, and there'll be work done against friction. Okay, so that's my final, my initial and my final. Okay. Once you've got that set up, everything should be positive. So if you know what's going where the energy comes from and where it goes to, that's the key to solving these questions. Okay, so I've got MGH, my work done against friction. Okay, so we know what do they want us to calculate? Find the work done against friction. Okay, so this is a work done by driving force. Okay, never mind. Work done by the driving force. We know power is work done divided by time. So work done is therefore equal to power times time. So I'm just going to say power times time, and half mv squared. And that's a half mv squared. And we want to know the work done by the friction. So I'm just going to leave that as it is. Okay, the mass. Let's fill in each of these. The mass is 1,600. Gravity is 10. Now we need the height difference. So I've got to zoom into my little triangle here. That's my height. So vertical height for potential energy must always be vertical height. So I know sine theta is equal to height over my length of my slope. That's 280. Okay, so my height is 280 sine theta. Oh, and we know sine theta is 0.09, so I'm just going to take that out. Okay, so that's just the potential energy. Now my power, 12,000, and my time is 10 seconds. And a half times my mass, and 24 squared. That's all equal to a half times 1600 times the speed at the bottom of the hill is 32 meters squared, and work done by the frictional force. Okay. Sometimes you can work these all out and then put them into the formula afterwards. I don't know why I quite like to do it all in one go, but it does get a bit long. Okay, 1600 times 1600 times 10 times 280 times 0.9 plus 12,000 times 10 plus half. Okay, and then subtract a half times 1600 times 30 squared. Make sure you can do all of these. All right, I am getting a final work done. Oh, that's correct. 164. 800 joules. That's correct. Okay, let's jump right into our next one. I just wanted to make sure that that was right, but it is correct. Okay, next question. So here I can immediately see forces and equilibrium probably. Right, a light string is fixed at A and has a particle of weight 80 newtons attached to B. A horizontal force of P is applied at B such that the string makes an angle of theta. Okay. It is given that P is 32 and the system is in equilibrium. Find the tension in the string and the value of theta. Okay, so all we're doing is because it's an equilibrium, our forces in our x and y direction cancel out. And let's just go with the force diagram. One thing that I'm going to do, I'm just going to rewrite my theta there. And I'm just going to show you, I don't need to do this, but basically I just erase the wall on that side so that I have a free body diagram that's just a little bit less confusing, I think. But yeah, obviously you won't have the luxury of just blotting out things with an iPad. So anyway, let's go. A light string, find the tension in the string. So sum of the forces in my x direction must be equal to 0. So I've got my theta has a component in the x direction. So minus my tension in my string sine theta, minus sine theta, and then I've only got p pulling it forwards. So those cancel out. So in other words, my p is equal to my t sine theta. And we do know that p is 32. Okay, so I've just rewritten that. I've plugged in my 32 and I took everything to the other side. Okay, now let's look at my sum of my forces in my y direction. Okay, I've got t has a component, so this is t by the way. T cos theta minus 80 is equal to 0. Those are the only two things I've got. Okay, so now I've got two things equal to t, so I can make them equal to each other. Okay, I've got one sine and one cos on each side. So if I multiply my sine through, that becomes tan theta. And we can then work out theta. So inverse tan of 32 over 80 is 21.8 degrees. Okay, and then because this is a simultaneous equation, I can then just plug in my theta. Let's just plug it in over here. So t is 80 over cos of 21.8. And that gives me an answer of 86.2 newtons if I look at three significant figures. Okay, so always either give more significant figures and then round off, or just make sure you are rounding off correctly. Okay. All right, now point B. Okay, so just the way that they set up the question kind of does make me wonder about point B, where I'm probably going to have to work out theta. Okay, it is given instead that the tension in the string is 120 and that the particle attached to B still has a weight. Okay, so now I know that this is 120. That's still theta. We don't know P now, and that's 80. So just redraw your diagram with what you do know now. Find the value of P and theta. Okay? System is in equilibrium. It is instead given that the tension in the string is 120 Newton and the particle attached at B still has a weight of that. Find P and the value. Okay, I'm just going to go with it. I imagine this particle is still in equilibrium. That's what I wanted to look for now. It would have to be though. Otherwise, it would have to give us more information, I think. Okay, sum of my forces in my x direction is 0. So I've got minus 120 sine theta plus p is equal to 0. Okay, and sum of my forces in my y direction is 0. So I've got 120 cos theta minus 80 is 0. Okay, so I can work out my cos theta pretty simply. So that's the inverse of cos, and 80 over 120 is 48.1 degrees. And then if I plug that into my p, I've got 120 times sine of my answer. I just use my answer button so that I don't lose decimals, and that gives me 89.4. 89.4 Newton. And that is that question. So what I find helpful here for part A and part B is in part A, draw your free body diagram, and then whatever information changes, redraw the free body diagram and just start again. Okay. All right, let's jump into question 6. A particle moves in a straight line, so kinematics. At the time t, the acceleration is a. Oh, it's given by that. Okay, so here acceleration is changing all the time. So it's varying acceleration. That's normally given by an equation of some sort. Okay. It's not constant. If it was an actual constant value, then you would be using Suvat equations. But because it is changing all the time, it means we've got to use integration and differentiation, and our velocity time graphs are going to have curves instead of straight lines. Okay, the velocity of a particle is that when time is that. So they've given us a moment in time. So when t is equal to 2, our velocity is 27. And we know they've given us a formula for acceleration. Find the value of t when the particle is at instantaneous rest. So that's when the velocity is 0. Okay, so when is this particle at rest? That's what we've got to figure out. Okay, and they want us to know the answer we're giving them is a value for time. Okay, so if you've seen any of my other videos, you will know that I've got this piece of artwork that I do. So when you're going from displacement to velocity, or velocity to acceleration, you need to differentiate. And if you're going up from acceleration to velocity or velocity to displacement, you need to integrate. Okay. So these things start to make sense if you just remember your IG formulas. You know, velocity is change in distance over change in time. Speed is change in distance over change in time. So that change in distance over change in time is basically looking at the gradient of a curve. Okay, but we're not looking at straight lines now. We're looking at curved lines. So we're not looking at the gradient between 2 points. We're looking at the gradient at a point, and that's why we bring in calculus, which involves differentiation and integration. Okay, so, and then just going down is 1, and then reversing it is integration. Okay, so we need to know when is this particle at instantaneous rest. So we need to know when is the velocity equal to 0. We've got an acceleration equation, and we don't want acceleration, we want velocity, so we need to integrate. And we just want an equation for velocity. So I'm going to do an indefinite integral, and I'm going to have plus c, and I'm going to have to calculate what is my c then. Okay. Now, 36. So you got to be comfortable integrating as well. You've got upper power divided by the new power. And here it's a definite integral, so we just have a plus c. Okay, now I'm going to plug in my time point. So they always give you enough, well, they should give you enough information to be able to do what you need to do. So in this case, I want to work out what's my value for c. So my velocity is 27. Plus c. Okay, I just simplified my 6 over 2 there. So I'm just going to do this in 1. 27 minus 36 times 2. And then plus. I'm giving you a value of negative 33. In my exam, I'd probably want to just be double checking that I am typing everything correctly into my calculator, but for now, I'm just going to keep going. So 36t minus 3t squared minus 33. So now I have a formula for velocity. Find the values of t. Find the values of t when the particle is at rest. Okay, so we haven't found when is this thing at rest, but we have got a formula for velocity, and what I need to do is make that now equal to 0 to find when is it at rest. Okay, so before I solve this, I'm going to divide everything by 3. It just looks like it's going to simplify my equation a bit. I might also rewrite this, so I've got a quadratic. I'm going to divide by minus 3. And that immediately helps me. I can see how to factorize that. So t is equal to 1 or t is equal to 11. So those are the two values at which my velocity is 0. Okay, so it's a lot of practice with this integration and differentiation, just picking up the keywords. That's really the crux of this topic. Okay, find the total distance. That is a big keyword. The total distance the particle travels during the first 12 seconds. Okay, so they've been very kind to us. Whenever you see the word distance, you need to realize that every time, okay, first of all, distance is not displacement. Okay, so every time you hear the word distance, whatever my velocity time graph looks like, if it crosses the x-axis, in this case it's actually the t-axis. If it crosses that axis, you need to break it up into sections of where it crosses the axis. If you were to integrate and get the area under this graph, and you just went from A all the way to the end, B, you would get displacement. Okay, we can't do that. So we've got to figure out, does it cross the x-axis? Does it cross the t-axis, I mean? And if it does, we've got to split it up into portions and integrate each one. Okay. Now, they've been kind to us because they asked us to work out the velocity. When is the velocity 0? So what we already know is this graph is going to cut at 1 and at 11. That is super kind. So we start at 0, we go to 1, and we end at 12. Okay? I just want to check one more thing. Our velocity is minus 3t squared plus 36t minus 33. Okay, so what I'm seeing here is it is a quadratic shape, but it's actually upside down, okay, because it's a minus 3. Right, so I was just giving an example earlier, but now I know that that's not quite right. You don't need to know the details of how this thing looks, but it is helpful just to have an idea. Ooh. Okay, I don't know exactly what I'm doing here, but okay, here's an idea. So I know it kind of crosses down here at minus 33, but that's not really relevant information. The more important thing is I know that it crosses at 1, and then it's going to be an upside down quadratic, and it crosses again at 11. That's what's important. So when I'm finding the distance is the area under the curve. And if we look over here, we are going up to distance, so we're integrating. But in this case, they want it in specific. They want to know what is the distance between these two times. So I'm not going to look for an equation necessarily. I'm just going to integrate each section. Okay, so my distance, let's just say distance 1, is the integral between 0 and 1. And that's minus 3t squared plus 36t minus 33. Okay, so I'm going to work out that one. And then I'm also going to do another one. Okay, so it's actually going to be the mod. It's the mod of that one. So whatever that answer is, I'm going to make it positive. Okay, I think let's just do one at a time. Otherwise, I'm going to run out of a way to write this down. So here we've got, if I'm integrating, minus 3t3 over 3, 36, the upper power divided by the power. Okay, and here we're going between 1 and 0. Okay, I'm not going to waste too much time. I can see if I plug noughts in here, it's going to be 0. So I'm just going to plug 1 in each time. So minus 1 plus 36 divided by 2 is 18. Okay, 18 minus 33, and then that's basically minus 0. So minus 1 plus 18 minus 33. Okay, so I get an answer of negative 16. So therefore, I know that the first portion is 16 meters. Okay, that's my first displacement. My second one is going to go between 1 and 11. Okay, and I'm integrating the same thing. Okay, so I'm going to show you a shortcut now on something. Oh, right, I already know the answer to this. So minus t cubed plus 18t squared minus 33, and I'm going between 11 and 1. Now, when I plugged 1 in, I know the answer is minus 16. Okay, so just take note of that. Minus 11 to the power 3. 33. There should be a 33t. 33 times 11, and then I say minus, and then I know my answer is minus 16. Okay, so the minus is important there. Okay, plus 18 times 11 squared. Okay, so what I'm going to do, I'm going to write down, before I give the final answer, this is 484, and then minus minus becomes a plus. That becomes plus 16, which is just 500. So the reason I wrote that down separately is because I'm probably going to use it now in my next step where I'm going between 12 and 11. I already now know the answer for 11, so that just helps. Okay, power 3, and this might even be symmetrical actually, so the answer might be 16 as well. But I'm just going to go with it for now. 36t minus 33t dt. Okay, I know this answer already. And now I'm going between 12 and 11. So if I plug in 12, it's 33 times 12, and then it's going to be minus, when I plug 11 in, is minus 484. Okay. Minus 12 to the power 3 plus 18 times 12 squared. 12, okay, so I get an answer of 732 minus 484. And something does not look 100% right. Okay, sorry, I got an answer of minus 468 minus 484. Okay, so I also get an answer of minus 16, so therefore 16 meters. Okay, and if I look at my total answer, I've got 16 plus 500 plus 16. And that gives me a total of 532 meters. Okay, so my trick for this question and my tip is to make sure you understand the graphs and the word distance instead of displacement. If they ask for displacement, you could easily just integrate and go between 0 and 12. Okay. All right, let's go. Last question. What does this want us to do? Connected particles. Okay, so particle A and B of mass 2.4 and 3.3 are connected by a light extended string. A positive is smooth pulley, which is fixed at the top of a rough plane. Okay, so this is most likely going to be going down. Let's just keep reading. The plane makes an angle of theta with a horizontal. The particle A is on the plane. Okay, particle B hangs vertically. It's 1 meter above the ground. The coefficient of friction between the plane and A is mu. It is given that theta is equal to 30 degrees. That's probably going to change in part B. Okay, it is given theta is 30. The system is in equilibrium with A on the point of moving up the plane. Okay, so that means friction acts down. Okay, and it also means that, well, it doesn't mean that, but our weight also acts down. Okay, so friction's going down, and we've got an mg sine theta acting down. Okay, show that it's on the point, it's in equilibrium on the point of moving up the slope. Show that mu is that much. Okay, so this is a connected particle question. Generally, you can split up the particles and we're looking at tension and acceleration. In this case, there's not going to be acceleration. So we can just look at tension, but they are wanting us to find mu. So I'm just trying to work out what is our unknown. Okay, so because it's not moving, that helps already. So if I looked at particle B, I mean, I can quickly work out my tension because it's just going to be opposite my mass, well, my weight. Tension is 33 newtons. Okay, this is only because it's not moving. As soon as it starts to move, the tension in the string changes. Okay, so then if I look at A is going up and down. We've got tension. I've got my friction and my mg sine theta. So now this is all in equilibrium. So minus mg sine of 30 minus my mu times my r plus my tension should be equal to 0. Okay? So I can work out this so far. So 2.4 times 10 times sine of 30. And then minus 33. Okay, so my mu r is equal to minus 21. So it's equal to 21. I took my other things to the other side. Okay, and my r in this case is just rx up, and it's just opposite the weight component acting down. There's no other forces in the y direction. So mu, and then r is going to be mg cos 30. Okay, so 21 over 2.4 times 10 times cos 30. 7 root 3 over 12, which is thankfully 1.01. No units. Okay, so we have been able to show the correct mu, which is always a nice feeling. Okay, next. It is given instead that the angle is 20. Okay, so it's lowering a bit, so this particle is now going to move. Okay, and that mu is 1.01. The system is released from rest with a string taut. Okay, I see an 8-mark question coming up. Find the total distance traveled by A before coming to instantaneous rest. You may assume that A does not reach the pulley and B remains at rest after it hits the ground. Okay, so it's not too complicated. What's going to happen here is that the particle is going to go up while it's connected to B, and then it's going to bounce. And that point here, the little bounce, is where it comes to rest instantaneously, and then it's going to go back down. Okay, so first of all, we just have to look at our connected particles. So if I look at B, I've now got my tension acting up, and I've got my 33 acting down. But I don't know what my tension is because it's now moving. Okay, it is going down. My direction of motion I take as positive. Okay, and then for my A, we have got minus 2.4 times 10 times sine 20, so my mass component, minus my friction, mu times my r, so that's 24 cos 20, plus tension gives me that. Okay, so in this case, I'm just going to make t the subject of my formula. So it's 33 minus 3.3a. Okay, and if I simplify some of this, because there's a lot going on here, I'm just going to get a value for t. Plus 1.01 times 2.4, well, times 24. Okay, so I'm getting a value of t, which is 2.4a plus 30.9866. Okay, I'm just going to keep my significant figures at the moment, and what I'm going to do is I'm going to equate these to each other. 9866. So 3.3 plus 2.4 is 5.7a, and that is 33. 866 is 0134. So my acceleration divided by 5.7, my acceleration is 0.353 meters per second squared. Okay, so when they combine, that's the rate they're moving at. So let's just find the total distance traveled by A. Okay, so A is going to travel a distance of 1 meter at that acceleration. Okay, so A starts from rest. It has an acceleration of 0.353. We need to know what is the final velocity at that point, and it's a distance of 1 meter. So it moves the same. If B moves down 1 meter, the string's obviously going to pull that up 1 meter. So here we have V squared is 0 squared plus 2 AS. So our final velocity is then 0.841 meters per second, something like that. So that's at the point, so it's already now gone up the hill. Now it's got an initial velocity of 0.841. We know it's got a final velocity of 0. We're going to have to calculate our acceleration or our deceleration and our distance. Okay, so the deceleration, let's now look at the forces on this particle. We no longer have anything pulling it up. We've only got our weight and our friction pulling it down. Minus mg sine 20 minus mu times r. Okay, so this is going to give us a new acceleration. That's 20 divided by 2.4. Okay, that gives us, I'm seeing that looks like quite a large acceleration. I just want to double check it, something doesn't look right. So minus 24 sine 20 minus 1.01 divided by 2.4. Okay, that looks much more realistic. So our acceleration is then minus 12.911 meters per second. So it's decelerating, which we could expect. And now we want to know the distance. So once again, v squared is u squared plus 2as. And our s is then going to be 1 squared 0.02739. So our total distance is then, let's just see what did the question actually ask. Find the total distance traveled by A before coming to instantaneous rest. Okay, so A travels 1 meter plus 0.027. So if we were to round that off to 3 significant figures, we would get 1.03 meters to 3 significant figures. Okay, and I think that is it. Let me know what you think about this paper. Is it a generally easy one or is it tricky? I hope that can help you, and all the best for your exams coming up.